Welcome to this Concept Explainer, brought to you by CBSE ScoreLab of ProfSam.com. Today, we're going to crack a very important and honestly a very scoring topic from Unit 4, moving charges and magnetism.
Okay.
We are talking about Ampere's circuital law. Now, I know what you might be thinking. Oh, God, Unit 4, so many vectors, so much integration.
That's exactly what I was thinking. The Biot-Savart law it's a nightmare.
It's the long cut, isn't it? Like building a wall brick by brick. So much calculus, very difficult math.
And half the time I get the limits wrong or mess up the direction. It takes forever.
Exactly. That's what we call donkey work when I do smart work.
Mm-hmm.
And Ampere's law, well, it's basically the cheat code for your board exams. If you understand this concept clearly, scoring marks here is very, very easy.
A cheat code sounds very good right now.
Okay, so before we get into any formulas or, heavy definitions, I want you to clear your mind. Forget physics for a second.
Done.
I want you to imagine a simple bathtub drain. You pull the plug, and the water starts swirling down. You can picture that, right?
Yes, of course. A little whirlpool.
Now imagine you're small enough to walk in a circle right around that drain. If you walk in the same direction the water is flowing, what do you feel?
I'd feel the water pushing me along. It would make walking easier.
And what if you turn around and try to walk against the flow?
Oh, that would be very difficult. The water would push back against me. I'd probably fall over.
Perfect. Hold that thought.
Okay.
Now, in electricity, we don't have water. We have
Current
flowing in a wire. But just imagine, around this wire, there is an invisible wind swirling. That wind is the magnetic field.
So the magnetic field is swirling around the wire like that water.
Precisely. And here's the wait what moment. If we can just walk around the wire and measure this invisible push, this magnetic wind, we can calculate exactly how much current is flowing inside the wire.
You're kidding.
Not at all. We can find the current without even touching the wire.
Just by walking around the outside, we can know what's happening on the inside?
That is the magic of this law. See, Biot-Savart adds up tiny, tiny pieces. DL, 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 DL. It's very slow.
The brick-by-brick method.
Yes. Ampere's law uses a powerful concept called symmetry. It's like taking one measurement of the whole boundary to know exactly what is inside.
Okay, the swirling wind idea makes sense. But how does that turn into a physics formula? You can't measure a wind in a notebook.
Good question. Let's build on that with another analogy. Imagine a river flowing straight. This river is our current, Obuckle Pass.
Okay, river is current.
Now you walk in a complete circle around this river. As you walk, you're measuring how much the magnetic field is flowing along with your footsteps.
So I'm basically adding up the push, I feel, as I complete the circle.
Exactly. And if you sum up all those little measurements for the entire walk, the total is directly proportional to the current enclosed by your path.
So if the river is huge, a high current, the total push is also huge.
Perfect. And if it's a tiny stream, the push is small. Big current, big field.
Okay, but I have a doubt. What if the river is over there on the left, and I decide to walk in a circle over here on the right? The river is outside my walking path.
That is a brilliant question. This is a classic point of confusion. Now visualize it. You're walking on dry land. The river's far away. Is there a magnetic field where you are walking?
Yes. The field should be everywhere, even if it's weaker.
Correct. But as you walk the first half of your circle, the field might be pushing you one way. Then as you come back around the other side...
Oh, it would push against me.
And what happens?
The push and the pull. They cancel each other out.
Bingo. If your loop does not enclose the current, the total circulation sums to zero. The law only, and I mean only, cares about the enclosed current.
Wow. So the field is there, but the total sum around the loop is zero if the current is outside. That's a very important distinction.
It is. Now that you have the intuition, the river, the walk, the enclosed current, let's bridge this to the technical side.
The part that gets the marks.
Exactly. Because in the board exam, you cannot write stories about rivers.
Yeah.
So let us see how insert defines this. Can you please read the statement for Ampere's circuital law?
Sure, I have it here. It says, the line integral of magnetic field beta dollar around a closed loop is equal to a one mole dollar times the total current passing through the surface. And the formula is, oh boy, it's an integral with a circle on it. Doint math BT, not money, mo, I-O.
I saw you hesitate there.
Yeah, that line integral around a closed loop part sounds scary. And there's a dot product as well.
Don't take tension. Let's unpack this. It looks like advanced maths, but it's really just simple arithmetic in disguise. Line integral just means adding up. Remember our walk. We're just adding up the magnetic field times each small step length. That's all that symbol means. Summation.
Okay, so it's just a fancy way of saying add up the steps. But why the dot product? Why math BFB HERFBS agamescentitle?
Think back to the bathtub. If you walk perpendicular to the water flow, does it push you forward?
No, it pushes me sideways.
Exactly. The dot product means we only care about the part of the magnetic field that is parallel to your path, the component of B that is helping you, or opposing you, along your direction DL.
Ah, so that's the $1 DL part. If I walk along the field lines, the theta is 0, cos 0 is 1, and I get the full push.
Perfect. And now for the shortcut, the cheat code. We're clever, we don't like difficult integrals. So for a long straight wire, we know the magnetic field forms.
Circles, concentric circles.
So if we cleverly choose our walking path, or Amperian loop, to be one of those exact circles, what happens to the angle theta between our path and the field?
Well, if I'm walking on the field line, I'm always parallel to it, so theta is always 0.
Correct. And what about the strength of the field B on that circle?
Every point on the circle is the same distance from the wire, so
Yep.
B should be constant.
Exactly. Because of symmetry, B is constant. And what do we do with constants in an integration?
We just pull them out of the integral sign.
Boom. The scary integral doint math BFB just changed. We pulled B out. Now we are just left with the integral of DL, which just means the sum of all the tiny step lengths. What is the total length of a circle?
The circumference, $2.
And the calculus has vanished.
Yeah.
The left side becomes just BLO multiplied by $2 times the current dollar. So our equation is simple algebra, BL dollars times 2 by L.
Wow, okay, that is actually really simple. We went from a scary line integral to basic multiplication.
That is the power of choosing a symmetric path. So if I want to find the magnetic field
You
B,
just rearrange it. Bile equals MUI divided by $2.
and that's the famous formula, bile my UI, took us 2 minutes. The same derivation using Biot-Savart is a 2-page nightmare.
I can definitely see why you call it a cheat code now.
Hope everything is clear so far. This concept explainer is from ProfSam.com. Now let's try a quick calculation. It's one thing to understand the theory, but doing the math is where marks are won or lost.
Okay, I'm ready.
Let's say we have a current dollar of 10 amperes. We want the field in a distance $3 of 1 meter. Use the standard value for 1 ampere, which is $4 times 10^7.
Okay, let me do this. The formula is $1 times naught. So on top, I have $4 times 10^7 times 10. And on the bottom, I have $2 times to naught.
Yeah.
Okay, I can cancel the $2 on the bottom with the $4 on top, which leaves a 2
Good.
And for the powers, I have $10 multiplied by 10, which is 101 1. So $7 plus 4 1 is 6 7. So the answer is $2 times 10 6.
Or the unit.
Magnetic field is in Tesla, so 2 microtesla.
Absolutely correct. See, the calculation is smooth, and notice the inverse relationship. The garter is in the denominator.
Right, it's a dollar relationship. So if
Right.
I get closer to the wire, the field gets much stronger.
Exactly. And a quick note, this law isn't just for wires. In our next topics, we'll study solenoids and toroids. Without this law, they are impossible. With it, the derivation is just 3 lines. It unlocks those concepts.
I will definitely remember that for the solenoid chapter.
Good. Now let's talk about the silent killers. These are the misconceptions that cause students to lose marks.
Oh, yes. Please tell me what to watch out for.
Silent killer number 1. Students think Ampere's law only works for circular loops.
But wait, didn't we just use a circle to prove everything?
We proved it is easy because it is a circle. The law itself, the equation doint math BFB IF I would, is true for any closed path, a square, a triangle, a potato shape. It's always valid.
Then why do we never use a square loop in the textbook?
Because we want to make our lives easy. If you put a square loop around a wire, is B constant on all sides of the square?
No, the corners are further away. B would be changing.
And is the angle between B and your path always 0?
No, the field is circular, but the path is straight. The angle would be a mess.
A horrible mess. You would have an integral you can't solve. So remember this. The law is valid for any shape, but it's only useful for symmetric shapes.
Okay, that's a brilliant distinction. Valid versus useful. So I can use any shape, but I should use a circle to save myself the headache.
Precisely. Now, silent killer number 2. Ampere's law is better or more accurate than Biot-Savart law.
Well, it's so much faster. I would have thought it was better.
It's faster for symmetric cases, yes. But they are physically equivalent. They give the exact same result. Ampere's law is a special case. Biot-Savart is actually more fundamental because it works for everything, even non-symmetric wires.
So never say more accurate, just say more convenient for symmetric problems.
Exactly right. Same result, different tool for the job. Okay, to help you remember all this under exam pressure, we need some memory anchors. First, the direction. We use the right-hand thumb rule.
Okay, the same one as before.
Similar, but with a specific application here. Hold up your right hand, point your thumb in the direction of the current, other dollar.
Okay, thumb is pointing up.
Now curl your fingers as if you are gripping the wire.
Fingers curled.
Your thumb is the current. Your curled fingers show the direction of the magnetic field lines, but they also tell you the positive direction to walk around your Amperian loop.
Oh, so my fingers define the forward direction for the integral.
Yes, if you integrate in the direction of your fingers, the current is positive. If you go the other way, you must use a negative sign for the current. It prevents all kinds of sign errors.
Got it. Thumb is current, fingers are the walk. That's a great anchor.
And for the formula itself, a simple mnemonic phase. B loop equals mu naught I.
B loop equals mu naught I.
Yes, the left side is the field times the loop length, so B loop. And the right side is 2 blocks times current dollars. So B loop equals $2 helps you structure the formula instantly.
B loop equals $1. I like that. It's catchy.
Good. So let's wrap this up with a 3-point summary for the exam. Point number 1, definition. Ampere's circuital law states that the line integral of the magnetic field B around any closed loop is equal to $1 million times the net current enclosed by that loop. Don't forget the formula. Doint math BFECSB DFVIEISB.
Definition and formula. Got it.
Point number 2, straight wire result. For a long straight wire, this law simplifies to find the field. 1/2 2 pi. The key takeaway is that the field is inversely proportional to the distance.
The dollar relationship, right.
And point number 3, application. We must use a symmetric Amperian loop like a circle for a wire to make the math easy. This is how we turn a hard integration problem into simple multiplication.
Perfect. Those 3 points cover everything.
Excellent. If you write this, you'll get full marks. So that brings us to the end of this deep dive. To get maximum marks in 12th CBSE Physics, Chemistry, and Maths, visit ProfSam.com.
That is ProfSam.
Yes,
Right.
ProfSam.com. Now, before we go, I want to leave you with a small disturbance, a little thought to puzzle over.
Uh-oh. Okay, what is it?
We said Ampere's law is doint B, currecido DL, DAO. It depends on the current other Bollinger dollars.
Correct.
Yes, the enclosed current.
Now, picture a capacitor being charged. A wire brings current to one plate, and then there's a gap, and then the current continues from the other plate.
Right, there's a vacuum or an insulator between the plates. So in that gap, what is the current dollar?
There are no moving charges, so I is 0.
According to Ampere's law, if I is 0, the magnetic field in that gap should be
0.
Exactly. But if you put a sensitive compass needle between the plates while it's charging, the needle moves.
Wait. What?
There is a magnetic field, even when there is no current.
But that breaks the law we just learned.
It broke physics for a while. The great James Clerk Maxwell saw this problem and realized Ampere's law was incomplete. He had to add another piece to it. But that is a story for the chapter on electromagnetic waves.
Wow. Just when I thought I finally understood something, I guess I'll have to tune in for that one.
That is the beauty of physics. For now, master this law, practice the right-hand rule, and you will do great. Good luck with your studies.
Thank you so much. This was really clear.